Good. I think I can already start with the introductions. Let's start. Thanks everyone for joining today's seminar from the Cambridge Ellis unit. I would like to start by thanking the sponsors of the unit for their support. We're really grateful. And today we have with us Gabriel Synnaeve. He's a research scientist at Meta, and yeah, he started at Meta, I think, in 2015, and before that he was a postdoc fellow at École Normale Supérieure in Paris, working on reverse engineering the acquisition of language in babies. He received his PhD in Bayesian modeling applied to real-time strategy games AI from the University of Grenoble in France in 2012. And he has programmed a bot that placed fourth in the AAAI 2012 StarCraft AI competition. And in 2009, Gabriel worked on inductive logic programming at the National Institute of Informatics in Tokyo. We have him today here with us, and he's going to be talking about multi-token prediction and exploring LM losses. I'm going to stop sharing my slides, and Gabriel, you can start with your presentation.
Great, thanks for the intro. Okay, so I'm going to eventually be talking about this paper, but there's a bit of a preamble before that. So yeah, so I'm going to be talking about multi-token prediction and also like what I think are interesting research directions in language modeling losses, and also in MTP. I think a bunch of stuff that we left, some basically stones we left unturned. This is mostly the work of Badr, Yubi Idrissi, and Fabian Blockle. So just want to say that foremost and thank them. Okay, so I start with very, very basic introduction, just so that we're all on the same page about LLM 101. So LLMs are made of transformers with self-attention. So self-attention is a softmax of key queries dot product with the value. We have multi-heads, so we can do a bunch of those in parallel, and we pay attention to when we basically encode the sequence so far, we pay attention to all the tokens before. The self-attention for each different head is going to give a different weight to the cross correlations between the tokens. And one thing I think that is interesting to think about and to know when we are thinking about LLMs compared to well, is that they're made of transformers, and how does it differ if they were based on RNNs? So in RNNs, you always, so the operation of predicting the next token, you always have an embedding for the whole state before the current token, which summarizes the whole past, right? So in terms of inference, it's very easy. You don't have this n square attention. You just have an operation which is O of n of the sequence if you want to decode, right? But when you're training, it's actually quite hard, because when you're training, you can't know at which tokens between 1 and k, which token between n and k is going to be important to predict, to remember, or to pay attention to, or to encode in your memory, if you want to predict a token n which is further beyond k. Whereas self-attention can do that in training, right? You can always, so that's how the gradient will flow, right? That's one difference. And the other difference is that the RNN computations always also requires you to have the hidden computed, so it's necessarily a sequential computation. Whereas self-attention, of course, it's this n squared that we said before, but you can compute everything in parallel, so you don't have this kind of comb graph. So it basically doesn't matter in the era of GPUs that you have this n squared in this case. Okay. Now, also, so that we're on the same page, basically this is how we design and how we train most LLMs that I'm going to talk about in the rest of the paper. We train them by, usually the baseline is we train them in teacher forcing on next token prediction. So you basically model probability of next token knowing all the previous tokens. You do that for all tokens and for a lot of text. And you do that with teacher forcing. What it means is if you have the sequence, beginning of sequence, the cats at on the mat, end of sequence, in your training, you're really going to have, I tell you this is beginning of sequence, what is the log likelihood over the next token, and we're going to optimize the NLL for the, right? And also I tell you BOS and the, what is the, and so we do that a teacher forcing way of training the models, because that's the only efficient way of training the models. And what we can see already is the way we train there is actually has like a kind of a discrepancy between the way we train and the way we do inference. The way we do inference is we have a prompt maybe, but then we actually start outputting tokens, and we output token n+2 knowing the token n+1 that we outputted, not the ground truth, and n+3 knowing token n+1 and n+2 that are also the ones that we decided to output, that we sampled from the model or that we took as argmax in an autoregressive fashion. But those are not the ground truth tokens for the answer, right? Also on the right, I put, Zoom is in front of me, but on the right, I put the basic schema of a block of all the kind of GPT style architectures, the decoder only transformer models, where most often you have a norm, a self-attention, a norm, and an FFN. It doesn't matter that much.
Question,
yeah.
One person is asking in the chat about the EOS and BOS. It seems it's end of sentence and beginning of sentence, no?
Yes.
They are like special symbols just to denote this. Is that right?
Yes. So usually in your tokenizer, you well, the next slide has a bit about the tokenizer, but in your tokenizers they map to one. They have a special index for those. Yeah. You have a few special tokens in your tokenizer. Yeah, so just like the basic architecture we use, self-attention, FFN. There's a bunch of normalization. No, I think it's more and more in fashion to have normalization before and after each of the layers. What matters there is in terms of computations. So in terms of computations, it's n squared for the sequence, m for the dimension of the model for the attention, m squared for the FFN, and n for the sequence. And actually, there's a big factor in front of this m square. So for relatively large models, the n square part doesn't matter too much as long as you're in short sequences like 4K tokens or 8K tokens, because the m is actually bigger for the biggest models. And also, what matters to know in those architectures is usually we have, let's say, m here, the hidden dimension for the self-attention, and you have something like 4m in the FFN. So basically, in terms of weight, here you have something on the order of m squared weights, whereas in the FFN you have of the order of 2 times 4m squared. So you have 8 times m squared weights. So you have way more in classical architectures, way more weights here to learn. So way more of the memorization probably happens in the FFN.
Can you clarify the FFN? What is it exactly? It's like a fully connected.
Yes, feed forward network. It's in MLP. It's the same thing. It's basically really 2 layers. It's the first layer that goes from the size of the output of the attention, which is dimension m, to something which is usually bigger. Most models it's four times bigger. Sometimes it's even more in some recent models. So let's say it goes from m to 4m. Then you have a nonlinearity. Which, for instance, in Llama is a 3 glue, in a bunch of other models is a Jolu or a Relu. And then you have another layer that is 4m to m, so that the output size of the FFN actually matches the input size of the self-attention at the next layer. So that's where most of the weights are.
Good.
Okay, and I don't know why I have this. Yes, okay. So because now, what we were saying, so the basics of a LLM, and this slide basically says the whole cycle of life for an LLM. So I did this when Llama 2 came out, but this is kind of still true today. Is what what are the steps to get an LLM from a very bird's eye view to get something that you can use in a chat fashion? Well, first of all, you have a tokenizer. And so, for instance, a tokenizer is something that is going to split the sequence in a bunch of different tokens. So in the case of here, I just did a small screenshot of the GPT-3 tokenizer, which is those are going to be the tokens you're going to get out of the sequence. This is a tokenizer. So tokenizer in the GPT-3 tokenizer is not a single token, for instance, right? You see it's token and a tokenizer. Why we do have that is because like you cannot have a lookup table for all the words that exist, because you can always invent new words, you know, first names, dates, bunch of like place names basically, and dates are like completely infinite. So you cannot have like a fixed vocabulary. So you do tokenize so that you have actually a mapping without unknown words. That's also, you do want to tokenize and not work on characters or byte at the smallest level, because you still want to reduce as much as possible the sequences, and you still want also the model to have to already have like a jump start in terms of sequence length and in terms of like what are the discernible units you have in your content. And so the plot on the right, it basically shows what goes into training a model. So for a Llama 2 model, for instance, so this is outdated, but this is still the true workflow. You pre-train for a lot of tokens. So that's where most of the knowledge is going to come from. This is most of the computation goes into. So you have this like 2,000 billion tokens that come from crawling the web, right? And a bunch of like public sources. And you train your 70 billion parameter LLM model, so your Llama. So this, for instance, back then roughly took 4K GPUs for 21 days to train this model. And then you have a pre-trained Llama 70B model. But at this point, this model, all it can do is, if you give it a beginning of a text, it's going to continue what is the most likely continuation for the text. And so if you want something that actually takes turns of speech and answers you, you need to fine-tune it to really teach it, okay, now when I give you a prompt, you need to give me the answer, not the continuation. And what we do for that is we do human annotations and fine-tuning. And for instance, for Llama 2, the number of tokens that went into this was 1 billion token, right? So this is a tiny amount compared to the pre-training dataset. And this you can train the model with this amount of data with 512 GPUs for 1 day. How do you get those tokens? Well, you could write down what you want in terms of behavior as that model and put that in the training set. But most often what we do is ask for human preference. So kind of RLHF, reinforcement learning with human feedback, a term you probably heard already, which is we use we have the model, the human asking the model something with a prompt question, and the model generates two different versions, either with different temperature and the decoding or different models, and then the humans pick which one they like best. We do that for a bunch of pairs. We form a training set. And the last phase of the model is basically really aligning it to the human preference. And it's rarely actually teaching it new knowledge, right? It's really more aligning it to terms of speech, to how we want questions to be answered. But you cannot put as much knowledge in the model when you have this ratio of compute between fine-tuning and pre-training. You know that you see there that most of the hammering on the weights of the model is going to happen at pre-training. So this graph is basically wrong in terms of numbers for today's models, but it's not wrong actually in terms of proportion. We have scaled up everything. The model size is probably the thing that has scaled up the less so far, but we have scaled up the pre-training, we have scaled up the post-training, but still you have much more tokens and compute going into the pre-training. Okay, I just wanted to say one bit about scaling laws, because actually they're going to come back at us and bite us into the work of multi-token prediction. So scaling laws, there was this seminal paper called Chinchilla, which I think now has been a bit, people look back at Chinchilla and say, well, Chinchilla was wrong because they only care about training optimality. but I think in the context that we were in back then, I think chinchilla was still a big term. So I will explain my situation. So basically, a position. So now we are, for instance, training Llama 3 8B, so 8 billion parameters with 15 tera tokens. And for 8 billion model, the chinchilla optimal law, which is what is compute optimal number of parameters and tokens to train. So if you set your number of parameters to 8 billion, the compute optimal number of tokens to train this model with is 200 billion tokens. But the chinchilla laws, it only considers training optimality. If you want to actually serve your model, your training computation, if you serve it at scale, the training computation cost is going to be dwarfed by your serving, so your inference computation cost. So in this case, you would need to redo the chinchilla scaling laws by trying to be training and inference, or training and serving cost optimal. And for this, you would find that actually overtraining, so training for way more than chinchilla scaling laws, is very important. So that is, I think that is become quite normal in the community to think that for like practitioners of LLM. But we have to remember that before chinchilla, basically what we had were models like GPT-3, for instance, which was 175 billion parameters. So here on the axis, orange one, which was trained with a few hundred billions. Which was trained with with also a few hundred billion tokens. So it was 175 billion parameters, but it was trained with a few hundred billion tokens. Whereas if you actually want to be compute optimal for the amount of training data that there was in GPT-3, you would train a much smaller model, something like 30 billion or something like that. So that was still a turning point, because the community was going on larger models without paying attention to put that much more data into it. And it refocused us on training on smaller models for longer, which is basically a trend that we double down or triple down on since then. Okay, so Llama 3.1 got released 2 days ago, so I had to add a few slides about that at the last minute, just to say. So I think everything I was talking about before still applies to Llama 3.1. This is basically a continuation, an evolution on top of Llama 2, where we train models for longer on higher quality and higher quantity data, and pay way more attention to the diversity and number of tasks you can do in post-training. But otherwise, there is no major fundamental change in how we do the science behind those models. So this is the table 2 from the paper, from the Llama 3 paper that we released 2 days ago. So Llama 3 is basically a family of models. So we have the 8B model, the 70B model, and the 405B model. So they're all vanilla dense model, very close to what I was showing before. They've been trained on multiple, I think the 70B, for instance, and the 8B are trained on like 15 tera tokens. So they've been trained pre-trained on a lot of tokens. And then we fine-tune with a bunch more preference data, both synthetic data and human collected preferences. We have a bunch of details about that in the paper, actually. So if you're interested about how this works, you should go read the paper. It's quite complete. Overall, what I want to say is it's just like better models, but it doesn't change the fundamental science of what we're going to discuss in the rest of the talk. So those are results on a bunch of benchmarks. I myself focus more on the code benchmarks in all my line of work, and that's what also the PhD students who did this paper did. So HumanEval and MBPP, and on this kind of work, we paid a lot of attention to the pre-training data, and also to fine-tuning with some feedback from the execution of the model of the code generated by the model. Sorry. And also a bunch of different tasks, like, okay, the task of code generation is not necessarily generating code from text, but it can be code from code. It can be generating tests from code, documenting code, a bunch of stuff like that, finding bugs. And across various model size, we have pretty strong performance on like a variety of benchmarks. So what they did in Llama 3.1 is actually also to perform scaling laws, but to decide how big we were going to make the biggest model. So what we did for that is basically looking at the validation loss, so on basically the log likelihood on some held out data for a given number of training tokens and for a given number of computes. And so when we do this isoflop curves, which are okay for same number of compute, should we train basically bigger models or should we train for more tokens? Because if you train for more tokens on a smaller model, it's still going to cost you in total same number of flops. If you do this kind of isoflops curve for a bunch of compute, you kind of find the optimum for each of this curve, and you can from this derive the scaling law between your purple points. And that's how we kind of extrapolated the size of the biggest model. And this is what you see in the middle. So those purple points on the left, they're here, and from this we fit a model. But you see we go to 1 to the power 22 here in terms of maximum flops for the scaling law. And if you extrapolate, you get to the 10 to the power almost 26 that was trained with the 405B model in terms of compute. And actually scaling law holds pretty well for what is going to be the negative log likelihood per character for a given fixed compute for a given size of model. Okay, now I'm going to talk about the multi-token prediction paper in itself. It was actually presented at ICML yesterday, so you should feel free to go check out the ICML page. And it's a joint work with Fabian, Badr, Baptiste, David, and Fabian and Badr are the expert matter in this paper. So the idea is basically how can we adjust the prediction difficulty for training LLMs? If you look at LLM, as I said before, trained in teacher forcing, a bunch of the tokens you have to predict are quite easy to predict. So if you look at the distribution over the next token given a given prefix, it's very often picky, right? It's not super often that the model has to really change during the course of training to really change the distribution. And so we looked at like what are the degrees of freedom we have to make this pre-training task more difficult. So one is the tokenizer size, right? And the tokenizer size is one way. So you could say if we increase the number of tokens, we'll have more and more things to more and more different tokens to choose from at next step. So more and more uncertainty about which token it could be by just default of having more tokens to predict from. And actually we worked on that, on trying to push tokenizers to their limit. And it's also a paper that we did at ICML this year. But this is this has its limits, right? And this is also something that was pretty well studied in the past, and the community kind of settled to tokenizers between 100 and 200K tokens of vocabulary for a bunch of practical reasons, but also for no return on downstream task performance if you go beyond. So what we did in MTP, so multi-token prediction, is to say, let's for a given fixed tokenizer, which was the Llama 2 / code Llama tokenizer, because our baseline is basically code Llama in all this paper. Instead of predicting just one token, let's try to predict multiple tokens. So for instance, here if we predict only four tokens as a target, what we mean is when we train, we're going to not just predict the n+1 token, so here it would be 2, and then 3, and then 4, and then 5, but predict at each step n tokens. So in this plot, n equals 4. So we predict n+2, n+3. So we predict 2, 3, 4, 5, and then 3, 4, 5, 6. Each step more looking further ahead in the future. And at first we were just looking into that as like a way to just train models. So we're saying, okay, we're going to train like that, and then we're going to discard the heads for future prediction, and we're just going to keep the autoregressive head, and we have the same as the baseline model, and we can really compare apples to apples. The way we did that is we took Llama 2 and code Llama models actually, and took the whole trunk shared for all the token prediction and just have different, the last layer, which actually is going to project into the space of the tokenizer. We have just different layers like this for each of the futures we want to predict for. So if we want to predict 4 tokens in parallel, we have 4 times this layer instead of 1 time. And a key finding of this paper is actually this. Initially, it looked like it didn't work. So initially, of course, we don't do experiments with that big model. So we do experiments with 300 million parameters model, for instance. And it looked like the code was correct, but things didn't work or even made the model worse. And so what we did still is say, okay, let's try and see how this scales. Let's try and do scaling laws for the impact of this loss when we scale up the model. And that was actually quite important, because that's what ended up making it work, is that actually for 2 small models, we figured out it was actually negative. It had a negative impact on the downstream task performance of the model. Whereas the biggest model, actually, it gives a boost over the baseline in downstream task performance, a significant boost. So here, MBPP is a code generation dataset evaluation. So it's mostly basic Python programs. So you are given the Python, are given a Python doc string, right, with a simulator of the function, and you have to complete. And then we know if it's correct by actually running unit tests that correspond to this program and to this prefix. So this is a hard benchmark in that it's correct or it's not correct what you generated. It's not like some translation where you can have different ways of make it being rather correct or incorrect. Here, like, you have many ways to generate a correct program, but your program has to pass the unit test. And so yes, that was the key finding, is that actually kind of our hunch was to say maybe the task is so much harder that the model needs sufficient capacity to be able to predict, to make advantage of predicting, for instance, n+3 or n+4 token. Because otherwise, like, the model doesn't have maybe enough capacity to be able to predict so far in the future. So that was one of the hunches that led us to do this scaling law. And so how does it look in practice? So usually you, so at the top you have the classical negative log likelihood, training loss of LLMs, which we use with structure forcing, which is predicting what is here xt plus 1, knowing xt down to 1. This is written always by looking at the last token first. And in our case, we look at the log likelihood of xt plus n up until xt plus 1, knowing x of t until 1. So if you decompose that, we basically sum over the log likelihood of the decomposition of t plus 1, t plus 2, t plus 3, t plus n, right? So that's as simple as it gets. Of course, already here you have a design choice, so you can decide how are we going to decompose the dependencies between the t plus 1 to t plus n tokens. So we did a bunch of ablations on either saying, okay, we're just going to consider them in parallel. So we predict t plus 1, knowing xt x1 to xt. We predict t plus 2, also knowing just x1 to xt. So in parallel, they don't have any mutual information between them, at least in the loss. And so that's this line, right, where we have head type, transformer parallel or head type linear parallel. And this is also what we called, and in the same case when you have n equal 1. And we also tried anti-causal and causal. Anti-causal is when you predict t plus 1 knowing what you sampled for t plus 2, t plus 3, t plus n. And causal is when you predict t plus n knowing t plus 1, t plus 2, t plus 3, whatever goes up to t plus n. And so what we found out is basically it doesn't matter much to do it in parallel. There's no significant improvement compared to the parallel architectures. At least what we looked at is well, in negative log likelihood, but also for the n+1 token, but also in downstream task of programming programming evaluation. So MBPP is the one which we saw before. HumanEval is very similar to MBPP, and apps intro is also a kind of intro to computer science type of programming tasks.
Can I ask one question here? Yeah. So I assume parallel is just, I mean, given the current state of the tokens that you have seen so far, you predict the next 4 tokens, for example.
Parallel, yes.
Independently. And then causal, my impression is that you predict the first token given the current state, but the second token is predicted using the current state plus the previous token. Is that right? Like
yes.
Embedding for that.
Yes. Yeah.
Okay. And then in what ways would this causal approach differ from?
Yes, it's a good question.
Training?
It's a good question. It's because we don't go through the whole we don't go through the whole LLM again. When the n equal 1 architecture parallel model, to do the n+2, you would put n+1 as input and go through the whole transformer again. Whereas here, it was really just for the head.
Okay. And then how do you get the embedding for the head for the n+1 token? Given that if you want to predict n+2, you will need like an embedding for the n+1 token. Is that right?
Yes. So you generate first the n+1. So you're going to generate n+1 to n+4, for instance. You're going to generate first n+1, put it as input to the head that generates n+2.
Okay, what you generate? Okay, yeah. So the generation for the
generation this way is autoregressive if you are causal, and autoregressive in the other direction if you are anti-causal, but at the level of the parallel prediction head.
Yeah, I see. Cool. Thanks.
Okay. So one of the issue of wanting to predict n tokens in the future is actually there is a significant memory cost at this last layer. Because we are projecting, because like for each head we are going to actually materialize the activations over like the 32K tokens of the tokenizer. So we have the M dimension times 32K, for instance, or in modern models M to 200K or M to 120K. This is significant. I mean, the activation that we generate there on the top is significant because you have that for the whole sequence. And what we did is just to compute the gradients sequentially and then accumulate them and update them once. And so this is a kind of a simple trick in what we did. On the left figure just corresponds to the code on the right, is we forward the whole shared model just once, and then we detach the tape. We are going to do for each of the head, for I in range n, so this is for each of the head. We're going to forward the head, do the backward on the head, and this way, like the model doesn't need to keep the autograd doesn't need to keep the activations, because once we have computed the gradients, we can remove the activations, and we just accumulate the gradients into Z, which is the shared model, which is where the bulk of the weights are. Remember, it's only at the last layer we do that, so all of the weights are in shared, and so we loop over those heads. We accumulate the gradient in shared, and once we're done, we just we need exactly the same memory as if we were doing single token prediction, and we don't take a cost of, instead of having if let's say the sequence size of big N total times 4 activations, while we just have the same sequence size of N in terms of cost of for memory for the N. This is just a computational trick, but this is exactly the same. We are optimizing exactly the same loss, and this is exactly the same computation as what was shown in the slides before. Okay, and now there is a small parenthesis on this paper, which is blockwise parallel decoding for deep autoregressive models. So this is one cool thing that this paper does, is basically speculative decoding, which is once you have a prefix, you can decode one by one autoaggressively, as LLMs do in general. But you can also say, let's decode faster. So you can decode a bunch of tokens at once and then just verify them. And that's also what we end up doing in MTP. It allows us to decode much faster. So let's say we have the prefix I saw a dog ride. Instead of predicting the in and then putting it back in and predicting the next one, we predict, for instance, if we have n equal 4, the next 4 tokens with the parallel prediction head. It doesn't cost us much. This is just inference. And then we can move by 4 tokens. By moving by 4 tokens, we will anyway verify. So we will anyway compute the likelihood over the tokens that we just added. And either they're correct, and then we have moved by 4, so we have moved forward quite a bunch. Or if they're incorrect, let's say the n+2 token was incorrect, we actually go back by 3 and restart this process. So if you do this, you have an exact decoding algorithm because of the verify step where you either accept or you move back your cursor. You have exactly the same inference distribution that you are doing that you are using for generating, but you can go faster.
How do you know that the tokens are correct in these settings?
You correct according to the model. It's like what I mean by correct is that you consider that what the n+1 head would have created generated is the correct token.
Oh, okay.
Right. So you don't know if what the n+2 head has generated would be the correct token if you move 1 token further and this was the n+1 head.
Mm-hmm.
Correct is basically according to the model that has the least hard task to do, which is the one of predicting n+1. Does it correspond?
And what for example, that the correct token would be the one that maximizes the probability, for example,
yes,
or
of the n+1 head. Yes, exactly. Yeah. So because those models before they were made self-speculative, they were made speculative by saying we have a very small model that is basically the hair that is running in front that is doing speculative decoding. It could generate like gibberish, and a slower, bigger model that is going to verify, which is much less costly than sampling from the model. And when the big model is in disagreement with the small model, we restart there for the small model and try and generate a different token, right? So this is a way to maximize the speed and the latency to which you get a correct token according to the big model by using on top of the big model a smaller model. Yeah. In our case, we don't need the smaller model because we can do self-speculative decoding. We can use the fact that we predict 4 in the future as a smaller model, and the n+1 as a big model. Mm-hmm. So those are, for instance, inference speedups. So if you use 4 heads, we have a relative speedup of 2.74. So it's almost, and on code is actually 3.05. So on code, what it means is 75% of the time you can move up by 4, right? If you average out. So it means 75% of the time you get accepted, right? If you average out. So that gives you a speed up kind of for free. So this is good. This is useful. Then you can look at, okay, if you don't necessarily care about being correct all the time, you can do a trade-off between speed and quality. So this is another paper that really studied that. If you want to know more, you should go read this paper. But basically, if you say, okay, I don't care that much that I have verified completely, what is the loss in quality I can take? So here it's a blow score for a block size, right? That I accept. So this is a trade-off you do, and actually you can get even if you say, okay, I don't want to be perfectly correct according to the big model, but I can get a bit of a loss. You can get even faster in this case, and you can get some speed ups still for quite long until like really the performance in terms of downstream task score. So here blow score falls off a cliff. Okay, and so let's go back on the scaling laws for this model. The fact that we said it works convincingly only at scale. So what we did then is to actually, for the first figure, this is basically looking into the details of the first figure I showed you for this, we trained 3B models from up to 3 billion parameters with 91 billion tokens. And we trained models for 7B and 13B parameters for 210B tokens. And what we see is like really the trend in average is consistent overall. And so here we have the different, so here we have pass at 1, pass at 10, and pass at 100. So this is also consistent over different tasks of generation. So pass at 1 is when you say, to consider that you pass the test, you can do only 1 generation. Pass at 10, you can do 10 generations for the given problem, and if one of them passes all the tests, you're considered correct. Pass at 100 is you can do 100 generations. And the boost that we see is like across the board holds and is statistically significant for the different pass at. So we also looked at what is the optimal n. And so we did that for a bunch of different domains, but basically here is it for code. So for code, on again the same data set as before, the same test set as before, MBPP HumanEval apps. We tried a bunch of n with different tokenizers. So either with a vocabulary at the level of bytes. So at the level of bytes, we don't have this tokenizer I was telling you before, right? So we have characters by character. In this case, the optimal n is 8, which makes sense. Those bytes are much smaller than tokens of the tokenizer, so you can probably predict more in the future. And this 32K tokenizer is the one from Llama 2 and from Code Llama. And in this case, the optimal n was 4. For most of the datasets, some of them it was a bit bigger. So we also looked at fine-tuning performance.
Sorry, so one question. What are kind of the trade-offs here? Obviously, if you have a larger number of tokens, I mean, training maybe is slower, but maybe predicting far ahead in the future is more difficult or so, and you can make more errors.
Okay, so there's no hard trade-off. If you could get away with strong downstream performance with a bigger n, we would do that, because it's always better. And as we with this computational trick, it's not necessarily more compute cost to train. Basically, what this shows is that past the number of tokens, the task becomes probably so hard that it's no longer informative for training. So if we were saying, okay, let's predict 30 tokens in the future with the tokenizer, with a given prefix, knowing n plus 29, n plus 30, right, is super hard, because those tokens, they will be exactly at this value, at this position. They will be very, very hard to predict so far in advance without knowing the text that comes right before.
Yeah.
So if we could get away with training n equals 32, I think we would like to do that, right? But basically the performance kind of degrades, and what you see here is n equal 1. We kind of degrade to the performance of n equal 1 for 8 tokens, kind of, on downstream task. So then if there's no gain, there's no use, right? Okay, and so we looked at fine-tuning performance. So if you pre-train with n token predictions and you fine-tune with n prime tokens prediction. So let's say if you pre-train with n equal 1 and you fine-tune with n equal 1, this is a classic case, the baseline. This is the pass at k you get for different. So this is the k, and this is the pass at k you get. Those are harder programming tasks. That's why the numbers are lower on the y-axis. Those are code contests, so programming contest challenges. So then we did also n equal 4 and prime equal 4, which is the use case you would have in mind usually. So you train on lots of code data, you fine-tune on programming contest, and you always use a setting where you predict 4 tokens in the future. And we also tried where you pre-train with n equal 4 and you fine-tune with n prime equal 1. So what this shows, this blue line, is that it's actually useful even if you just care about it for pre-training. You can say, I just will pre-train with multi-token prediction, and then I will do what I usually do with my model, so I will discard those future token head. You retain this gain when you when you train with when you fine tune with n prime equal 1. So what it shows is basically compatibility with the original kind of standard training pipelines. Then we did some experiments in natural language where it's a bit less clear where it helps. So those are some accuracies on classic natural language benchmarks. Here, actually, the token prediction is slightly it starts to be slightly impeding as soon as you train for long enough. And in the case of translations and summarization, I think this one was summarization. So making the text a smaller text, in this case, you do have a small boost. So kind of a high-level observation we made is when your task, and those tasks on the left are basically multiple choice answers. So the answer you have to give is just one token. So for giving an answer like that, it doesn't matter to predict more than one token. Whereas for those tasks for which it helps, like summarization and like code generation, the output you're expected to give is like a full generation with a bunch of tokens. So in this case, it's like you have a long text and you have to resume it in a paragraph. And in the case of code generation, you have a prompt and you have to generate a bunch of code to solve the test. We also did some math, grade school math or simple math kind of benchmarks, for which we saw some help across temperature. So temperature is what you use to sample, right? So you can sample greedily, which would be temperature 0, or you can sample by saying we're going to put a bit of temperature in our softmax, and this way you have more different generation, which is, for instance, necessary when you want to do pass at 100. And in this case, we saw a boost of doing MTP on some of the math benchmarks across. So this is pass at 10 and this is pass at 100. So what this shows is that in pass at 1, the boost is for lower temperatures more than for high temperatures. And as you go towards pass at 100, the difference between 1 and n tokens actually decreases, and then like the boost in this case is like really in the other direction. What we have is that for the math problems, as they are also like the NLP benchmark I was telling you about, which is about caring about a simple answer, the discrepancy is the other way around. We don't have a boost. We have a slight cost of doing multi-token prediction in the downstream task, and the cost is the same, but actually moves around the temperature, because when you do pass at 100, the higher scores you're going to get for higher temperature. Okay, and then we did some toy tasks. So for instance, here, this one is induction herd learning. So this toy task was actually done on real data from a validation set, but in what we call induction learning is if in your prefix you have the string AB, for instance, how much more likely are you to output B if in your prefix you also have A? So if the end of your prefix is A and then previously in the prefix you had AB, how much more likely are you to output B as a continuation? And we did this with real 2-token nouns. So it's not like it's not a completely artificial task. It's just we search for 2-token nouns that appear in the prefix and in the continuation, and we look at the induction success with MTP models with the baseline and with MTP models of n equal 2. And what was interesting is that actually for small models it helps the induction. So basically for small models, training with by predicting token n plus 1 and token n plus 2 helps with induction, and it starts to get to basically get drawn out in noise when you have models above 100 or 300 million parameters. We also did tasks of polynomial arithmetic, which is another type task. So it was about solving polynomials that were relatively simple. So the training set, we sampled a bunch of random polynomials with up to 5 operations. So that is what we train on, and that is what we test on with bigger polynomials. And we did that with baseline and MTP. Actually, there you do have a boost for solving the polynomials. And what is actually interesting is we did that also for different sizes of models. So it's the same graph as before, but here we were showing just the n for a given size of model. But here we're showing both the n with the colors, and with the glyphs we're showing different model size, so 30 million or 100 million models, parameter models. And the change in loss you have, the change in accuracy you have for predicting the polynomials is more explained by the MTP. There's a bigger change by using the MTP than by using larger models. So larger models are better, but models trained with MTP and equal 4 are better in a higher fashion than larger models. So now we kind of, this was interesting, but we basically don't know exactly why it works. So we have made some speculations and some attempts at explaining that. The high-level reason of why we think it works is that it mixes between this the train time teacher forcing distribution, what I was showing before, that when you train, you're predicting only the n+1 token, and you know the ground truth of tokens up to 1. Whereas when you do inference, you actually sample, right? So when you're going to predict n+1, you're going to know the prompt, but n+2, you're going to know only what you sample for n+1, and so on and so on. So that's basically the root of the explorations we did for explaining why it works, is saying, well, actually here we are not going to predict just n+1, so we're going to try to model the distribution of tokens beyond n+1, and maybe this helps the model know more the actual distribution that it's going to have to look at when it does inference, rather that is a bit different than the one from training. And so it also could be more data efficiency, and we have a bunch of data points showing that it may be more the impact, the data efficiency of training with this loss. We have two discussions in the paper, one on the look ahead reinforces choice points, which I'm going to go into now, and then a kind of information theoretic argument for why this works better. So multi-token prediction boosts the weights of hard transition in the loss. So that's basically the first hypothesis, is if your ground truth is 1, 2, 3, 4, 5 AB, and your model predictions goes like that. So if you have a multi-token prediction loss, you are going to assign higher implicit weights to what we call the consequential tokens. So the consequential token here is A, right? Because probably in nature and distribution, the most likely tokens after 1, 2, 3, 4, 1, 2, 3, 4, 5 is 6, right? So that's the one with, I would say, the most surprise, right? So one way to see that would be to say, if you have only an n+1 loss, only autoregressive loss, you're only going to have the loss for predicting A wrongly after 5 once in your training. Whereas if you have an MTP of 4, A actually appears 4 times. It appears when you are at 3 already. You have to predict A, otherwise you're going to get the loss. At 4 also, at 5 also, and then of course when you have to actually predict it, when it's n+1. So that's kind of one key idea of, like, basically if predicting the tokens is really easy for most of the tokens, but some key tokens are choice points where the model is really uncertain, we should put way more weights in the training on those tokens, but we don't know ahead of time. So how can we do that? We can have this kind of MTP loss. And actually this observation, this kind of intuition seems to be correct, but because I don't know if you remember at the beginning, I was discussing about self-speculative decoding, and we have a speed-up factor of 3, self-speculative decoding, which basically means that 3 out of 4 tokens are very easy for the model to predict, right? So that's kind of the parallel between those two. So that's been studied by a very interesting paper which is called The Pitfalls of Next Token Predictions by Barman, Gregor, and Nagarajan, which are also really studying that, like, okay, if you are a token, you start at 31 here, you have different paths you can go down to, right? And let's say those are easy tokens, and this is a difficult token. If you make the wrong choice for your difficult token, you're on the wrong path if you are in a purely autoregressive loss. Whereas if you actually have to predict as a unit further ahead, you have this look ahead, maybe you will avoid taking those kind of surprise wrong choice tokens. So we have a bit more explanation about this in the paper. Basically, our other view is the information theoretic view, and this one is also I think quite high level and not super rigorous either. But if you look at the loss of the entropy, at the entropy of next token prediction. So here in this notation, X is the next token, and Y is the token after next. And we just compare next token prediction with two token prediction. The entropy of H of X is H of X knowing Y plus I of XY. If we look at the entropy of two token prediction, it's H of X plus H of Y. So it's H of X knowing Y plus 2I XY plus H of Y knowing X. So the H of Y knowing X, you don't care that much because this one over a whole sequence is going to telescope, right? So it's kind of going to be just a trailing factor at the very end. But what it means is that for each pair of tokens that you're going to have to predict into token prediction, you increase the weights of the joint prediction on X and Y. So what I mean by that is, yes. So basically, what continues to matter once you have predicted the X is still the Y, while you put 2x more weight if you are predicting two tokens. If you look at the entropy of the sequence, and related to this, we are like
just one note. We're almost out of time. Do you have many more?
I'm almost done with the main paper.
Okay.
Yes. Cool. So why is this main matter is basically, okay, we're training on n tokens. We are basically training on n views of the data. And it may simply matter for languages that are inflectional languages, for instance. So like if you look at German, this sentence, for instance, you need to read it almost like right from left, because Göttingen is actually going to tell you Ziel, which is going to tell you minor, which is going to tell you Durchstanden. So the fact that you're looking at a bag of token by looking at n plus k tokens is going to give you more freedom to work on those languages where like the dependencies are much less left to right than English. And it's also maybe just making the training more data efficient. Okay, so I'm going to go fast about this, but basically this is the last meaningful slide. Is we also tried to train for longer. So in training data, we went for 1 tera token. And in this case, when you train for 1 tera token, you have some cases where you still have a gain for the multi-token prediction. And some cases where actually the n+1, so the autoregressive baseline, starts to be better. And so that would support the hypothesis that it's maybe just a more efficient data, data efficient loss, because you're actually seeing more of this smoothing and more of those choice tokens more often in the training, but eventually the autoregressive models could catch up. Yeah, so this is what it says, is that if you scale the training, so autoregressive classic training scheme actually works well. So in conclusion, it works. What it means is it's useful. It's useful if you want to do self-speculative decoding, so have tokens faster. It's useful if you want to do more data efficient training. It works better or even starts to work on bigger models. But we don't know exactly why it works, so maybe it's just more data efficient training compared to the current trend of overtraining. And we have some hypotheses that would need further exploration for why exactly it works, what are the mechanisms, and more research is needed in this direction. And I'm done with the main part of the talk.
Cool.
Any questions?
Thanks. Yeah, maybe I can ask a few questions. We're a bit out of time, but we can have some quick ones. One of the reasons why I could imagine this also helps is this idea of multitask learning, where sometimes you do multitask learning in machine learning, where you have maybe a big model, and instead of training it on one task, you train it on two tasks or more tasks simultaneously. And sometimes you feel that this helps. And this usually, the bigger your model, the better, the more this can help, which kind of aligns a bit in terms of the results that you obtained. And you have here clearly multiple tasks. No, like one task is to predict one token, two tasks is to predict the second token, the third token, the fourth token. So maybe that could be also some ideas why this could also help.
Yes, totally. I think there is a direct link at pushing more information into the weights of the model faster. And for that, your information has to be not completely collinear. Otherwise, it doesn't help the model, because we are all training with like Adam and stuff like that. So it really has to cover more of the ground of the gradient space, use the gradient better. And I think that's also what may be happening when you do multitask prediction. It may be also sometimes in multitask prediction that most of the settings for this, it may help regularize the models, whereas the datasets are not as big. But here, I think the dataset is big enough that we don't need regularization. So it's really the factor of data efficiency or learning this kind of trace tokens.
Cool. We're out of time now. Thanks a lot for your talk, Gabriel, and thanks everyone for joining. And I'm looking forward to seeing you at the next seminar. Thanks, everyone.
Thanks.
Bye. Bye-bye.
Richard, do you want to ask your question after time?
Oh, yeah, sure.
Yeah, it's fine. I can take 5 minutes. Yeah, no problem.
Great.
Yeah, go ahead.
So in the time series literature, as I think you guys pointed out in your paper, these tricks are like used all the time and have been for quite a long time. And one of the things that they end up doing there, especially these big transformer models for weather, is they combine it with curriculum learning. So the horizon over which you're predicting forwards extends with through training, basically.
Yeah.
I guess that's a massive fiddle for the LLMs, but is that something?
No, it's something we could be doing. I think it's something we could be doing, but the only problem I would see is a bit of an optimization issue. Actually, we did something like that. So we tried to we wanted to try MTP on much bigger models, like 70B plus even.
Mm-hmm.
And the problem is we couldn't afford to train this model from scratch.
Yeah.
So we tried to do continued training on those models with multi-head. And if you try to do continued training by saying we take the n+1 head and we duplicate it, this doesn't work that well. It's a bit unstable in terms of in terms of training.
Mm.
If you try and start training by saying I only take the n+1 head and I'm going to initialize n+2, n+3, n+4 randomly, then you get very, very different gradients. So like the numerical instability of optimization arise again. So what ends up working is actually saying, don't matter, we're going to we're going to restart all the heads, even the n+1 head, and do some more burnout more burning of those, and retrain the head completely from scratch in the continued training. So the problem is if you wanted to do kind of smooth, continuous curriculum learning by adding more and more heads, I think you would be confronted to the same problem. And so we would either need a way to kind of say we're going to do a new head by doing some averaging of the other heads so that they have like the same scale and the same kind of initialization. Mm-hmm. So we will need to find kind of a practical way of doing that without having to retrain from scratch the head all the time whenever we grow it.
Yeah, so the time series approach usually is to sort of put film layers in and you condition the whole network on a lead time. Often vision transformers, so it's not like got the same structure as you, but so the architectures end up being a bit different, and it's often not handled by multiple heads. It's handled by actually multiple architectures, which are all film variants of one another. I wonder if that makes it easier in their case, but they certainly do. Like you start off like predicting short term, often the runs random, and then you slowly sort of grow this through training. And they also end up doing like an ultra aggressive schedule as well, like a rollout schedule. The parallels are kind of interesting. I think there everyone thinks it's like the multitask learning is sort of the argument for why it's working. But it'd be super interesting to explore the things you sort of expanded on.
Yeah.
That also applies.
Yeah, I agree. Yeah.
Thanks for the talk. It was great.
Thanks. Will, you have a question?
Yeah, sorry. So I was wondering whether you could think about an architecture that could dynamically scale this. So would it be that you had some kind of supervisor that decides how much extra token it could predict, and you could use the context of the text, like knowing whether it's doing a multiple choice question or not, to know whether it will only do that one token or whether that more rich context